Welcome back to section 4, where we're going to look at hyperbolas. One of the things that we're going to see is that hyperbolas, which are these green guys, are actually amazingly similar to ellipses that we just finished looking at. I know they don't really look similar, but the similarities are incredible, and we'll see that in just a minute. But first, we're going to look at the learning targets, which are similar to the learning targets for ellipses. I can write the standard equation for a hyperbola, and I can graph a hyperbola and identify its vertices, covertices, center foci, and asymptotes. The only thing different here from ellipses is the word hyperbola instead of ellipse, and hyperbolas have asymptotes and ellipses don't. So, with the similarities, let's look at the similarities between ellipses and hyperbolas. First of all, the definitions. If we recall the definition of ellipses, it's the set of all points where the sum of the distances from the point to two fixed points, foci, is constant. The hyperbola definition is the set of all points where the difference of the distances from the point to the two fixed points is constant. So instead of adding the two distances together, we're going to subtract them. That's the only difference in the definition. So if we remember what an ellipse looked like, it was m plus n. If we had any point, we have our two foci, and m plus n was always going to equal the same number. In fact, it was always going to equal this distance, the distance of the major axis, which in this case is 10. For a hyperbola, if we take any point on the hyperbola, let's pick this one, then this distance minus this distance is going to be the same. If we call one of them m, the other n, m minus n is a constant. And notice I have it in absolute values, because if we switch the order, it would be negative instead of positive, or vice versa. One of these, this one over here, is going to be n minus m, and this one over here is going to be m minus n. But it's all still the hyperbola because it is. So we just need to do the big one minus the small one, or make it positive afterwards. So, very similar, very similar. The equations are even very similar. The basic equation for an ellipse, we're not getting too into it right at the moment, x squared over a squared plus y squared over b squared equals 1. For a hyperbola, x squared over a squared minus y squared over b squared equals 1. Ellipses have a second equation, a squared minus b squared equals c squared. Hyperbolas also have a second equation, a squared plus b squared equals c squared. This actually is the Pythagorean theorem. And that is a little bit trickier to see on here than the ellipses were, but it does come directly from the distance. As I mentioned, the constant sum is going to be this distance, the distance between the two vertices, the distance of the major axis. The constant difference is, again, the distance between the two vertices, this closest distance. Because if we took this dot and put it right there, well, we have this distance, and we have this distance. If we go this distance minus this distance, that just takes away this piece, and we're left with just the stuff in between. And so that's going to be the distance. And it's, again, going to be 2a, just like here was 2a. So let's take a look at these hyperbolas. Just like with ellipses, we have horizontal and vertical ones. The horizontal ones open horizontally. The vertical ones open vertically. We have the foci, just like we did with ellipses. We have vertices, which are going to be right where we think that they would be, where they would be if it was a parabola. Notice in hyperbolas, the focus is further away from the center than the vertex, where in an ellipse, it's closer to the center than the vertex. We have covertices. The covertices are going to go the other way. So there and there, and then for vertical, they go horizontal. Notice the covertices aren't actually on the hyperbola. They're just kind of floating out in space. Well, we're going to use those in a second. But first, let's talk about our axes. In an ellipse, the one connecting the vertices was the major axis. It was the longer of the two. In a hyperbola, it might be longer, it might be shorter. These might actually be the same. That doesn't make a difference. But if it was shorter, calling it a major axis is kind of seems strange. So we give it another name. We call it the transverse axis. It's still just the line between the vertices, and then vertical as well, the transverse axis. Well, then the line between the covertices is obviously going to be called the conjugate axis. These aren't as important to know, but they're there. So conjugate axis, and here conjugate axis. Now, how are we going to use these guys? We are going to make a box, a rectangle, that hits both vertices and both covertices. And what does this rectangle do? Oh, and by the way, that's basically the same if these are the same points we'd use to make the ellipse out of. Instead, we make a rectangle. And the rectangle, if we draw lines through the corner of the rectangles, those are the asymptotes, because hyperbolas are asymptotic. So we draw a rectangle, draw lines through the corners, and those are the asymptotes for the hyperbolas. The slope of the asymptotes for horizontal, we go up this distance over this distance. Just like with an ellipse, that would be up b over a. So slope is b over a, and negative b over a. Looking over on the vertical, we can draw the same box. We can make the same axes. The slope, we go up b over a, and up b over negative a. So the slope is always plus or minus b over a. Now, the book, again, does this one a little bit different, where they always make the vertex distance a and the covertex distance b, just like they did with ellipses. And in ellipses, I said that was stupid. In hyperbolas, it's even more stupid. Don't do that, because it changes the equation for the asymptotes as well as every other equation that we are working with. I would just leave a as your horizontal distance and b as your vertical distance. And so let's look at the equations. Oh, before we look at the equations, let's look at distances. That horizontal distance I mentioned was a, and same thing, a. Vertical distance is b. Vertical distance is b. Again, the book changes that up. I wouldn't. And then the focal distance is c still. Focus distance is still c. And c will be the biggest of the three. Now we should be able to look at some equations. The basic one for the horizontal, centered at 0, 0, is x squared over a squared minus y squared over b squared equals 1. If we wanted to move the center to hk, we're going to do the exact same thing we've done everywhere time else. X minus h squared over a squared minus y minus k squared over b squared equals 1. The points for the vertices and covertices and focus are identical to ellipses. Same exact formulas. So I'm not going to write the formulas out here because, as you saw with the ellipses, a lot of times it's easier to look at the graph and just kind of almost figure it out as opposed to plugging in the formulas. but you should have the formulas in your notes already. So horizontal, it's x squared minus y squared. Vertical, it's y squared minus x squared. And so we have y squared over b squared minus x squared over a squared. This is still the vertical distance. This is still the horizontal distance. If we wanted to make it a center not 0, 0, y minus k and x minus h, both of them squared. And so, as I mentioned a little bit earlier, it doesn't matter which is bigger, the A or the B. In fact, they could actually be the same. What matters, what determines whether this is going to be horizontal or vertical, is which one of our variables is positive. The y squared is positive, it's vertical. The x squared is positive, it's horizontal. And so that's the important thing. Because other than that, we're going to graph these identical. If we had this equation that made this, but it was y squared minus x squared, the box would be the same, the asymptotes would be the same. We would just graph it in this area and up here instead of in the horizontal areas. So we have these equations that are the same for both horizontal and vertical. The one that deals with the focus, a squared plus b squared equals c squared, and the asymptote equations. If it's centered at 0, 0, y equals plus or minus b over a, x. b is underneath the y, a is underneath the x, makes our slope, y and x. If we want to move it to a different center, a center hk, we can plug it into point slope form. Y minus the y point, k, equals plus or minus b over a times x minus the x point, h. Notice this looks just like this or this. So if you have a center somewhere else, well, hey, it's y minus 2 squared. Well, this is going to be y minus 2 equals plus or minus b over a x plus 3 squared. This is x plus 3. They're the same because transformations work the same whether you're dealing with a conic section or a line or a polynomial or an exponential function or pretty much anything else. So that's one of the beautiful things about transformations. But anyway, these are the equations for asymptotes, both at centered at 0, 0 and centered at h comma k. And again, the formulas for your vertices and covertices and foci for both horizontal and vertical are identical to what you have for ellipses. So now that we have all this vocab, what are we going to do with these? We're going to do pretty much the exact same thing we did with ellipses. We're going to find the constant difference. So if we have a couple focal points and a point, we're going to find the distance from one focus to the point minus the distance from the other focus to the point. So distance is x minus x squared plus y minus y squared, then square root. Distance, x minus x squared plus y minus y squared, square root. So we have the x's and the y's. Notice all the y's are 0. So as we saw with the ellipses, we could just say, hey, negative 13 to 5, well, that's going to be 18. 13 to 5 is going to be 8. Those are the two distances. We'll find those this way too. Negative 13 minus 5 is negative 18 squared. Zeros are 0. Here, 13 minus 5 is 8 squared. Zeros are 0. Negative 18 squared is positive something square root is 18 minus 8 squared 64 square root is 8. 18 minus 8 is 10. So notice since it's only the x values, this was 18 and this was 8, and there we go. We're subtracting them. If this was an ellipse, we'd be adding them. What else are we going to do? We're going to write equations in standard form. So we could be given some information, a center, a vertex, and a focus. And so here, we need to figure out first, are we going x squared minus y squared or y squared minus x squared? Is this going to be horizontal or vertical? So we look to see our center, our vertex, our focus. What variable is changing there? Oh, the y variable is changing. So if our vertex is in the y direction, that would make it a vertical hyperbola, which means we have y squared minus x squared. Center 0, 0, so we don't need to worry about anything with the y or the x. Now we just need b squared and a squared. Well, b, the vertex, is going to be here, so that's just going to be 5 squared minus a squared. We don't know a yet, but we do have that equation, a squared plus b squared equals c squared. We can plug this in for b, and 13 is c, so we get a squared equals 5 squared plus 13 squared. We can square both these numbers to get 25 and 169. Subtract 25. A squared equals 144, which means a equals 12, but we just need a squared anyway. So we can plug the 144 into there. 5 squared is 25. And there's our equation in standard form. So again, things to make sure of. We have the y squared minus x squared correctly, because the vertex and focus are in the y direction. The co-vertex would be in the x direction. It's perpendicular to it. Then we plug in what we know and use this formula to find everything else. How about if we had a graph? Same idea. We have a center, and then we have the horizontal radius, we have the vertical radius, and in this case, we can see it's horizontal, which means we have x squared minus y squared. It's centered at 0, 0, so we don't have to worry about the numbers there. And then, let's see, a, now these are counting by 2's. We get to 7.5, or we get to 7 both ways. So that'll be 7 squared. And b's is 5, so that'll be 5 squared. And then 7 squared is 49, 5 squared is 25, and we get that equation. And so notice this is pretty much the same as dealing with an ellipse, except with an ellipse, this box would just be elliptical. Other than that, it's the same. And then graphing hyperbolas, that's going to be very similar to graphing ellipses as well. So it's probably gonna ask to find some pieces, vertices, co-vertices, and asymptotes, and then graph. So if we start out with one at 0, 0 for a center, we have x squared over 36 minus y squared over 49 equals 1. Well, our vertices, it's horizontal, so we're going to change the x value. We're going over 6 both ways. So starting at 0, 0, we're going to go backwards 6 to negative 6, 0, and forward 6 to positive 6, 0. Co-vertices, starting at 0, 0, we're going up or down 7. So we're going to go 0, 7, 0, negative 7. And the asymptotes, we're at 0, 0, so it'll be y equals plus or minus a slope times x. The slope is b over a, 7 over 6. So y equals plus or minus 7 over 6x. Now, amazingly enough, we're not going to use those really to graph it. Well, we will, but we don't need to think about the points. If we have our graph, we start at 0, 0. Our x radius, or x distance, is 6. So we can go backwards 6 and put a point, forward 6 and put a point. Our vertical radius is 49. So we can go 7, so we can go up 7, put a point, down 7, and put a point. Now, that's the exact same thing we do with ellipses, except with ellipses, we'd now connect them. With a hyperbola, we now draw the box. So we have our box, and we can make our asymptotes through the corners, and then graph it. It's horizontal, so it'll be here and here. It's going to hit the vertices. It doesn't come down here. I start at the vertex and go out towards each side, start at the vertex and go out towards each side, and make it asymptotic with the asymptotes. And there's the hyperbola. Not much different than graphing an ellipse, except that it looks entirely different. But when you see the other stuff here, you can see where it's very similar. So let's try one more. We have x minus 4 squared over 9 minus y minus 3 squared over 64 equals 1. So here it's not centered at 0, 0 anymore. If you would like to, go ahead and give this one a shot. You can probably graph it. It would be good for you to try. Did you get graph paper? You should really use graph paper for this. It'll make it a lot easier. I'll wait. Alright, now do you have graph paper? Did you graph it? I'm telling you, the graph paper is going to make it easier, but alright, if it's in your notes, whatever. So, you graphed it? No, you didn't graph it. Come on, try and graph it. Did you do it? No? Alright, well, I give up. It's your notes, it's your success. If you graphed it, good job. To the rest of you, shame on you. So we're going to start out by finding the center. The center is 4, 3. And our horizontal distance is 3. So from the center, we're going to go backwards 3 to 1, 3, and forward 3 to 7, 3. The vertical distance is 8, so we're going to go up 8 and down 8 to get to 4, 11, and 4, negative 5. Then the asymptotes, we're going to have the slope is plus or minus 8 over 3. We're going to have y minus 3 equals plus or minus 8 over 3 times x minus 4. Because remember, this and this will actually go right there into the equation. Get our graph. Let's start at our center, 4, 3. Now we're going to go over 3. So start here, go over 3, go over 3 this way. We can go up 8 and down 8. Draw the box. Draw our asymptotes through the corners. And then this one is again a horizontal one because we have x squared minus y squared. So starting from here, we'll go up and down to make our hyperbola. So, how close was yours? Oh yeah, those of you that didn't get it, you missed the opportunity. Or those of you that didn't try it, missed the opportunity. We'll have more in class. We will definitely be graphing at least one of these in class, so come prepared. And I will see you then.